The diagram that you see up on the board right now is of something called a cyclotron. A cyclotron is one type of particle accelerator. Typically what we do with this is accelerate charged particles, usually subatomic charged particles like protons, to incredibly high speeds, and then we smash them into something, oftentimes another proton or some other subatomic particle. Now, why would we want to do this? Well, last year, my family went to the Drumheller Royal Tyrrell Museum in Drumheller. My son, who was at the time 5 years old, we bought this little Dinosaur Excavation Kit. Okay, so it's basically like dinosaurs in plaster of Paris, except it's a little harder, right? And so what do? You take this little hammer and this little chisel and you chip away and you find these toy dinosaur fossils in there. You could also, if you wanted to, I suppose, just take it and huck it down on your driveway and break it into a million pieces. When we break this thing up, no matter how we break it up, okay, we discover what's inside it. Well, we discover what makes it up. So why would we want to smash protons into each other? Maybe to see what makes up protons, to break them apart and see what makes up the protons. But here's the thing with protons. They don't want to break apart. They're so tightly bound together that they just do not want to break apart. So we have to get them going really, really high, incredibly high speeds. Like we're talking speeds that are approaching the speed of light, so that they have enough energy to overcome those forces that keep them together. It's kind of like your car. If you want to break your car up to find out what's inside it, okay, to see, pieces going everywhere to see what's in your car, two cars in a parking lot that hit each other at 7 kilometers per hour, let's say, maybe scratch the bumpers. Right? You're not going to find out what's inside when two cars at 7 kilometers per hour crash into each other. If two cars are moving at 110 and collide with each other head on, then the pieces go everywhere. You see what makes up the car because of the high kinetic energies involved in that collision. It broke apart the car. If we accelerate these subatomic particles to crazy high speeds, then we're going to see what makes up these subatomic particles, because at that energy, they break apart. Does that kind of make some sense? Now, how exactly do we get them to such high speeds to break them apart? Well, this is where the cyclotron comes in. We inject these subatomic particles or ions usually into the middle of this cyclotron, so right here. Now, these ions or these subatomic particles will accelerate across a potential difference. There is an electric field in this little gap right here. There is an electric field which will cause charged particles to speed up, right? It's like EI equals EF. Remember potential energy converted to kinetic energy? It's like the car going down a hill. The charged particles will speed up a little bit. It'll speed up till it gets to here. And then it's no longer in the electric field. So what happens to it? Well, now it's in a magnetic field. What's the shape of the path of a charged particle in a magnetic field? Circle. So it goes in a circle, or at least a half circle, until it gets to an electric field, which causes it to speed up, to accelerate. And then it gets to another magnetic field, which causes it to go in a circle. And then it gets to an electric field, which causes it to accelerate, speed up, and then a circle, and so on, and so on, and so on. Now, this doesn't look like a circle, right? This looks more like a spiral than a circle. Can anybody explain that one to me? Like, why is it spiraling out as opposed to going in a perfect circle? Yeah? That's right. It's going straight, and what's it doing as it goes straight in the electric field? Okay, but because it speeds up, right? As it speeds up in the electric field, now the radius is going to be bigger. If we take a look at the equation that describes it when it's in the magnetic field, R would be equal to mv over qb. As v gets bigger, as v is bigger, then R is bigger. So every time it crosses that gap and speeds up, the radius is going to get bigger. So if we look at this, that's a circle. And then it goes at a constant speed, then it speeds up, and then it goes in a bigger circle. And then it goes or accelerates, and then it goes in a bigger circle, and so on and so on and so on. Make sense? So These charged particles, they speed up every time they cross one of these gaps with the electric field, go in a circle, and then it speeds up again and so on, till it reaches a crazy high speed, and eventually it's just allowed to leave and then hit something, hit a target, hit another charged particle, or whatever it is that it's designed to do. I got a couple questions for you here. First one, which way is the magnetic field acting? Which way is the magnetic field acting in order to cause these charged particles to go counterclockwise like this? I'm going to give you a second to think about that, okay, at your desks, and then I'll see if somebody can come up with the answer. Which way is the magnetic field? Not the magnitude of it, because we don't have any numbers in here, but which direction is that field acting to cause the motion that we see there? All right, so let's take a closer look at this. In order to find the direction of the field, what we can do is look at the motion of the particle at any given point. At any given point, we know that the particle is moving at a tangent to the circle. So right here, the particle would be moving this way. Right here, it would be moving this way. Right here, it would be moving this way, a tangent to the circle. Okay, let's look at the first position that I drew here. Let's say at that point, this positive particle is moving toward the top of the page. So let's stick our right thumb toward the top of the page. Which way is the magnetic force acting on this particle at that point? We know this. Which way is the magnetic force acting if the particle is moving this way? Towards the center of the circle. How come? It's moving in a circle. There has to be a centripetal force toward the center of the circle, which is provided by the magnetic force. So we would say thumb in the direction of the particle, which is toward the top of the page, palm in the direction of the magnetic force, which is toward the center of the circle, thumb, palm, fingers point which way? Into the page. So the magnetic field there would be into the page. Now, if you were to do that somewhere else, like let's say right here, we would get the same results. Thumb down and to the right, palm toward the center of the circle, fingers are still going to point into the page. Does that make sense? Magnetic field pointing into the page. Now, one more question. We've already established that this is how I would analyze the problem as a charged particle goes through the magnetic field. How would I analyze this section of the problem right here? How would I deal with that when the charged particle goes through this electric field to speed up? That's like a car doing what?
Drifting.
Not quite. Could be. Down a hill, which would not be a good idea.
Kidding? Would drift, I think, well,
When a car goes down a hill, it speeds up, right? That's what's happening here. These charged particles speeding up. When a car goes down a hill, we would say, initially at least, we would say when it starts from rest, we would say mgh, or qv, equals 1/2 mv squared, right? Now, what if we analyzed it up here, going across this gap up here? That would not be qv equals 1/2 mv squared. That would be qv plus what? Somebody said it. Plus 1/2 mv squared equals 1/2 mv squared. Why the extra term up here versus down here? What's the initial speed right here when it's injected into here? Zero. So it's got just potential energy. What's the initial speed when it's going across the gap up here? Something, not zero. So it's like a car right here at the top of the hill, but already moving at the top of the hill. Make sense? We were going through this morning, and then it occurred to me, like, man, this would make a great written response question, wouldn't it? Like a great electricity/magnetism written response question. And then I thought, actually, like, hey, what if charged particle come out here and then hit something, and then collide it with something? We could make that even better then, right? We could make that like first 3 units, momentum electricity and magnetism all on one test. So I might have to, I did take a note of that this morning when it occurred to me, so see what ends up happening with that.